Hello and welcome back to question number 3 on the 2012 Manitoba Mathematical Competition. We have two parts to question number 3. 3A, a circle has an area of 5 square units. That's a little odd. Usually there's a factor of pi there, but okay, no worries. Circle has an area of 5 square units. A square is constructed around the circle so that each side of the square is tangent to the circle, just like we have here. A larger circle is constructed around the square so that it passes through all 4 vertices of the square. Find the area of the larger circle. Okay, so we know the area of the smaller circle. We just need the area of the larger circle. All right. Well, let's, as we do, draw our picture. Draw the big circle first. There's our square. All 4 vertices are on the circle. And then we have inside here our smaller circle. Okay. So, now, things that I read in the question, in particular, the sides of the square are tangent to the circle. Now, when I think tangents and I think circles, the first instinct of mine is to connect up those points of tangency to the center of the circle, and that'll give us radii. Okay? So that's what we're going to do, and I think that's probably the first instinct of just about anyone. Okay? So, we'll get red out here, and we'll connect up these points of tangency. They all meet at the center of the circle, and they all give right angles to the line that is tangent to the circle. Okay. And so, since we've got a square here, we know that these are all right angles as well. We can start writing some of this down. Connect the center of the smaller triangles. Not triangles. Center of the smaller circle. Don't know where my head is. By radii to the points of tangency. And that makes right angles. Okay. Since the square has right angles, we can see, oops, wrong color again, or wrong thing again. We get right angles here. So we get so each of these lengths is the same. It's all the radius. We might even call this radius r. But because all these right angles, these must be rectangles. Rectangles whose sides are all the same length. So we get side length r, the smaller radius. Okay. So that's all nice. But we need the area of the big square, or the big circle. Okay? So how do we get area of the big circle? Well, we need its radius, pi times the radius squared. So I might say something like, let r be the radius of the big circle. To compute the area, we need pi r squared, so we just need to figure out what this r is. Okay. So, what to do? Well, the center of the smaller circle is going to be the same as the center of the bigger circle. There's a number of ways we could phrase that. I think it's a little obvious, so I'm not going to bother touching on it, but if you thought it was necessary, if you think it's something that should be added in, and if you want to, you can check out their solutions. Click the second link. It'll take you to their main page for the MMC. If you think it's something that should be added, you could easily say something like the big circle is circumscribes the square. If you circumscribe a square, the center, or really if you circumscribe any regular convex polygon, the center of that regular convex polygon coincides with the center of the circle. And so you get the center of the big circle is the same as the center of the square. Not hard to show that the center of the square is the center of this smaller circle. Right? Pretty clear from our picture, since all those little squares of radius little r are the same. But I think it's obvious, so I'm just going to state that. Okay? So the center of the big circle is the center of the square. Were this a later question, I might add in more details here, but it's question 3. So I'm not going to dwell on it a whole lot. So that means if I connect up this point, the center will have big R here. So we got a little triangle. I'll highlight the triangle. I'll underline it in green here. But this triangle is what we're talking about right here. So it's a nice little triangle there. We get R, it's a right angle triangle. And now we have a relationship between little r and big R. And that's useful because we can derive little r, because what are we told? We're told that the small circle has area of 5 units. Well, 5's got to be pi little r squared. So we can work out what little r is, or little r squared. And then we can work out capital R squared. Pi capital R squared is going to give me the area of the big circle. Okay? So, r squared plus r squared is big R squared. Or rather, 2 of the little r squareds is big R squared. We know that 5 is pi r squared. So 5 over pi is r squared. So twice 5 over pi, which is just 10 over pi, is capital R squared. And the area of the big circle is pi capital R squared, which is pi 10 over pi, which is just 10. It just doubled. Not bad at all. And if you wanted to, again, you could make a little therefore statement, but it's nothing we're going to particularly worry about. It's question 3. We're not being the most rigorous, but everything we need for an explanation is there. And that's all that they really require. So that was A part. Now we've got B part here. A rectangular tank has length 2 meters, width 3 meters, and height 3 meters, and is full of water. A cylindrical tank has radius 2 meters and height of 3 meters, and is empty. Water is siphoned from the rectangular tank to the spherical tank. The siphon will stop flowing when the depth of the water is the same in both tanks. What will be the depth at that moment? Okay. Interesting. So we've got some dimensions to consider. Length 2, width 3, height 3. I'm going to draw a picture here. We're specifically asking for the depth, right? That particular depth. What will be the depth at that moment? let h, you could use d for depth. I'm going to let h for height. So I'm going to draw some pictures over here. So we have a rectangular tank. And at the start, it's full of water. Cylindrical tank, which is the same height. Radius 2, we got 2, we got 3, and we have 3 here. So at the start, this thing here he's full of water. Okay, and then water slowly gets siphoned. And at the end, we're going to be left with these things, and they're both filled up to the same height. Again, 2, 3, but we're going to have up to a depth of h. So the amount of water has to be the same. So we start with a total volume of 2 times 3 times 3. That's 18. What is it? We're measured in meters, so meters cubed of water. We might say something like this doesn't change or this is conserved. So we can see at the end, that moment where the depths are equal, it's got to be the same amount of water. So 18 meters cubed has got to be the same as 2 times 3 times h plus the amount of water over here in the cylinder. Same depth. And then it's, well, this is going to form a cylinder of water in here of height h and radius 2. So it's going to be pi 2 squared h. So that'll be 6h plus 4 pi h. Okay. So what can we do? Well, we can factor out the h's over here. 6 plus 4 pi. Going to be the same as h. That's got to be 18. Okay. So we just divide through. H is 6 plus 4 pi. It's 18 over 6 plus 4 pi. That's the same as h. One thing I can do, I can take out a factor of 2 on the top and bottom. And that's really as small as we can make it. So I would probably leave that. If you're a person who cares about units, you could say meters. But it's not going to be that important. Just double check. 2 by 3 by 3. 2 by 3, again, the height. 2 is the radius, and then by 3, water is siphoned. We just care about when the depth of water is the same in both tanks. So, what will the depth be? It'll be 9 over 3 plus 2 pi. We leave it exact. There's nothing we can do. Okay, we don't have calculators, so we couldn't grab it and approximate it even if we wanted to. It's not like a Cayley contest where they give you to the nearest half meter or things like that. Nope, we just need exact answers. That's what we got. 9 over 3 plus 2 pi. And we're ready for question number 4. We're going to take a look at that in the next video. Thanks for watching.